All right. I guess that is having shelter is slightly more important than calculus.
Slightly.
Just barely.
Just slightly.
Yeah.
Just barely. All right.
I mean, really, you wouldn't have that shelter without calculus, so.
Pretty much.
Is it? I could build a little mud hut without calculus.
Yeah, I like a little like.
I would hope so.
Surprises.
A little shanty.
They've
town.
been building houses since
Okay.
before
Okay,
calculus.
guys.
Yeah.
Any questions from homework and stuff? Are you guys trying the homework out?
Yeah, sure.
I finally posted officially the module that had the blank polar coordinate graphs. If I don't click the little thing, you can't see anything. So that was fantastic. So that's been done. And I posted the practice final.
Thank you.
I decided not to print any out. So it's up on Canvas though. So if you need a copy printed out for you, just come to my office tomorrow. I can print it out because then I could use the school's ink and paper. It's fantastic. So if there's no questions from homework, we're just sort of going to continue in the direction we started. There's a couple things to finish with parametric stuff, and then we'll get into polar coordinates. And again, polar coordinates are freaking cool as hell. So are parametric. I mean, the shapes you can make, and we're sort of playing with it a little bit, were we?
Yeah.
Remind me? Okay, because I'm teaching the exact same thing right now, just without the calculus, obviously, in my pre-calculus course. We're doing polar parametric. And I showed them the butterfly equation, all that kind of stuff. Okay. So parametric, you would have something like x of t, y of t. So let's give us some stuff here. In fact, let me steal one from the book, sure. I like it. That's what it says. Yeah. Okay.
This is still.
So if you had to plot this by hand, what would you do?
Make a
Make a
T,
chart.
X, Y.
Yeah, make a Tixie. Tixie winner. Right, T, X, Y table. So normally we only need X and Y because X was fed into Y directly. The reason that these graphs can be so much more interesting is because I've given myself more freedom now. T is kind of controlling both, so it doesn't have to be a function. It can kind of go back on itself. It can go all the way around. It can all do all kind of weird things. Okay, so let's do this. Let's see if we can make a quick TXY table. And I don't just want to use 0, 1, 2. You guys agree? That's not really good enough resolution for this. So let's at least use the half points. At the very least. Okay. So what's at 0? What's x? 0. And what's y? 0. Holy shit. Okay. I can even do the quarter points, but let's see if this is enough. I think I told you before, you might not choose enough values for t, so you might have to throw some more things in between to get better resolution. But let's see what we can get. At 1/2.
It's gonna be what? One.
Yeah, sine loves it at pi over 2.
And, 3/4.
Yeah, 1/2 will be 1/4 plus 1/2, 11. 1/4 plus 1/2 is 1/4 plus 2/4 is 3/4. Okay. And real quick, you know what it would do at 1/4. You know what sine would do, right?
Yeah.
Sine pi over 4. You add 2 over 2. Anyone know what the square root of 2 is?
1.3 or something?
1.414. So the square root of 2 over 2 is about 0.7. That's good enough for doing something by hand. You guys understand me? So it's really kind of good to kind of carry some of those around with you. 1, 0, 0, 2, 2. 3/2.
That'd be negative.
Negative.
Yeah, that's down here. Sine likes y, but this is negative. 3/2 will be 9/4 plus 3/2, 9/4 plus 6/4,
15 fourths.
15/4, which is also 3 3/4. Is that right? Yes, sounds good. So like 3.75. Nothing amazing here, right? I was like, there's never anything amazing here, Jeff. Cheers. 2,
0.
0,
6.
6. I love it. Kick ass. All right, so let's kind of give this thing a rough sketch. When I sketch parametric curves, what should I really kind of be in the habit of including as I plot the points? I'm pretty sure we talked about this. Everything's melding together with my other class.
The arrows?
Yes, the arrows, the direction of motion. I like it, just in case. It's good to get in the habit.
The arrows at the end or throughout the whole?
Throughout the whole thing, yeah.
Oh.
Yeah, or you just need a couple places really, because they just follow. Unless it's one that kind of goes, then you probably want more. Trust me, that is a picture of an actual function. Or something close to it, right? So you probably want a few more arrows to help somebody along.
What do
Okay,
you do?
this is also a map of streets near my house in Virginia Beach, because that's insane. Wow.
What do you do if a function comes back on itself? You know what I'm saying?
What do you mean?
So
what do
it
you
comes
do?
this way initially, and then it takes the same exact track. Comes back.
Backwards.
Yeah.
What's really cool is, well, I don't know if you guys would agree with me, if it does this and then it kind of goes backwards,
Yeah.
right? Well, then you just have arrows going both ways indicating.
Yeah.
Yeah. That's why you try to truncate the domain to eliminate that retracing. Yeah, and be more specific about at what moments are we interested in, when the particle's going this way or when it's going the other way. Okay, good question though, because that does happen. If I try to, well, okay, we'll get there. Get ready in. So let's graph this real quick. So we got 0, 0. Can we do this? Did I do this? Okay, do that from my brain. 4 little brain. 0, 0. Let's make a scale. Well, X is easy. And Y, I need to go up to 6. 2, 4, 6. That's easy enough. I think you can do that. Weehaw. Okay. Negative even? No, just
No.
X. Okay, I like it. Negative 1, 1. 1 3/4. Be right there, so I can kind of connect those. 0, 2. You can make whatever sound effects. Negative 1 3.75. And then 0, 6. Well, let's get out of there. There. Okay. Nifty. Okay. Looks like the House of Drell. Superman. Yes.
Yeah, in the top right corner, what is that weird symbol next to the D?
Oh, does anyone know what this means?
Between.
TN?
Yes, I like it. An element of. Or you can just say in. I like it. T's in there. T's in this thing. I like it. All right, so nothing too major. This should be relatively easy. It shouldn't be that big of a step away from stuff we've done in the past. And real quick, if things were going too big, I would go back and put a 1/4 and so forth if I needed more resolution. Right? Yes.
So in the textbook, when it was like graphing things, it included T for the points. Do you want us to do that as well? It'd be
Oh,
like
it would put
0,
the
parentheses, 0.
T value next to it. It depends on the problem you're doing. It could be useful. Well, all right, we'll see which kind of problem. I got to think about that for a second. Because sometimes you want to know where two different. I don't think this happens for us. I could have this parametric. This is one parametric set, right? I could have another one, and I could say where do those meet, and it depends on if they have at the same time, right? It's sort of like if I walk through a park, and somebody else walks through the park 3 hours later. Did we meet?
No.
So we would meet if we're in the same place at the same time, right? And so that gets even niftier. If I have two separate parametric equations, I want to know when they meet. You guys kind of with me a little bit? All right, so we'll get there. We're good. Blah, 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 blah. Okay. So now let's ask a couple of questions. Can you figure out the derivative? Can you figure out the slope of this curve.
Yes.
Okay, how do you do it?
Take the derivatives of it's gonna be dy dt
dy dt?
over dx dt.
Dx dt. Algebraically, doesn't that just make sense?
Yeah.
I could divide the top and bottom of a fraction by anything I want to as long as it's not zero. By definition, dt is not zero. Whew, there's a lot to say. Is everybody cool with that? Right? That's what we talked about last time, I believe, yes?
Can you explain why the second derivative of dy over dx is...
We'll do a second derivative, and I'll show you. Yeah, the book shows it, but I want to really show you why it makes sense. Good question, though. So we'll do a second derivative for this. What's dy dt? Nice and easy. 2t plus 1. Dx dt?
Pi cosine pi.
Yeah, dude. Pi cosine pi t. If anybody's wondering why there's pi there, why is there pi there?
Chain rule.
Chain rule. I love it. Okay. So far, so good, right? So what if I want to know, let's just do this problem. Where'd it go? Blah, blah, blah. Oh, I see. I misread it. Okay, that's fine. It'll still work out. So I want to know the slope, I want to know the derivative at 0 to this point. And did we go through that point? Yes, we did. Sweet. That's useful.
Can you take the derivative if it didn't go through that point?
Of course, well, no. It has to exist there, of course, right? But that might mean I just didn't go far enough with my t. I saw 0 2 and I thought they meant that was the interval, but it still works for us. What do I need to feed the derivative to figure out the slope at a point? What does it want from me?
You create it.
What variable's in here?
T.
T. So I can't put a 0 or a 2 because what do these represent?
The x
X and Y. When do I have a point of 0 2?
At t equals 1.
That's equal 1, right? What if it wasn't in your table?
And you have
How could you figure out what T was?
Put it in the table.
I don't know. If it's not in my table, I don't know. Maybe T is 1.111173.
Solve for x. and
Yeah,
y.
so sine pi over T must equal 0, while T squared plus T has to equal 2 at the same time. You'd have to solve that system of equations. Thankfully, we got it. Right? But do you understand what I'm saying?
Yeah.
The derivative will be a function of T. So if they give me an XY point, I can't use that word shit. I need to figure out what T makes that happen. That's what this needs. Like it?
So we have two sets of coordinates for the xy value.
Two sets of coordinates.
Like if we have 0 2, then we have 0 0 and then 0 6. Or if we want to use it like the x values.
Oh, no. Are you looking at all the places where X is 0?
And 2. Yeah. Wait. No. Wait. Okay, never
So
mind. I'm really
specifically it
confused.
has to be this point, and I only hit this point once.
Okay. Oh. Okay.
Now, a really good question would be, what if it turns back and it hits that point again? Well, then it has two different slopes depending on the time it was there, correct? You guys thorough with me?
Okay.
What if I'm climbing a mountain, right? I'm climbing a mountain, and I go through this point there, straight up. And on the way down, I'm going diagonal, right? Because I'm being careful. Am I not going to go through that point at a different slope? On the way up, I'm like that. On the way down, it could be like that.
Mm-hmm.
Totally different slopes, right? So it depends. If I go through, all right, did I go through 0 2?
Well, if you're going down the slope.
Did I go through 0 2?
Yeah.
Yes. Slope is positive, right?
Yeah. So no matter where it
Couldn't
is,
one of these do this kind of thing?
it would be negative.
So you have two different slopes through 0 2 depending on when you go through it. Do you guys see that?
Yeah.
So the problem wants a specific answer. It has to be specific. If it just said 0 2, you're like, I'll give you two answers then, problem. Right? At t equal this, it's positive. At t equal that, it's negative, whatever. You guys sort of with me? That kind of relates to an earlier question.
The repeating one.
Yes.
Yeah.
Yeah. Okay.
Because it would be negative if it like went past the same line, kind of oscillating on that one path.
By the way, okay,
Positive.
exactly. By the way, is this a function?
Of y?
I like it. This is a function of y. Is this a function?
No.
No. It's not a function of x or y, but it is a function of t.
Yes.
At any given t, I'm at one place. Do you understand what I'm saying?
Yes.
at any given time. Now, I was physically at that point twice, but at any given time, I'm only in one place.
So just input output.
Yeah, if I consider my input to be t, it actually is a function of t. For every given t, there's only one point that comes out. You guys with me? Okay. Thank God. All right, that's not, I won't say anything else. Okay. For right now, that's the way it is, and that's the way it's going to be for us. Okay. Let me just stop. I keep going off on little tangents because there's nifty stuff on the side of this. So pretty cool with what we've actually done so far.
Yeah.
You should be able to make a TXY table. You should be able to graph it. You should be able to give me arrows. You should be able to figure out if there's not enough information. I mean, if my points are like here and then there and then there and then there, I might want to do some more values of t in between just to make sure where the hell it really is. Okay, maybe. And again, that's all about resolution. Okay. So, JJ, you wanted to talk about second derivative. So watch this. This is really cool. Isn't this just y prime? Isn't the second derivative just the derivative of the first derivative? Okay. So how do I do dy prime dx when I do the same exact thing?
Yeah.
So wouldn't that be dy prime dt over
Dx prime.
no,
Just dx.
dx dt? Yes? Yes? Is everybody cool? I'm doing exactly the same thing I did. dy dx, dy dt dx dt. dy prime dx, dy prime dt, dx dt, right? That's it, right? Okay, I'm gonna keep going. I'm getting a weird vibe. So now here, I just take this guy's derivative, and that guy's derivative is gonna be, what would I have to use to do it?
Quotient.
Well, sure, no, I don't want to do that. Do you guys want to do that? Is that enough of an answer?
I thought it was the derivative of dy over dt over dx.
Over dx dt. It's this, yes.
It was something obscure, wasn't it?
So let me show you what the book's got written. And I'll show you it's the same thing I've got written. Here it is. Bum, 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 bum. Oh, yeah. Are you guys concerned about? So here's what they have written exactly, and it's exactly what I have written. They have this. Yes, and this is page 650, right?
Yeah.
This is what they have, which is exactly what I have. What is dy dx? Isn't that y prime?
Yeah.
Okay. Right? So just remember, the second derivative is nothing new. It's just a derivative of a function. If I know how to take the derivative of a function, I take the derivative of a function. Now, because I'm taking the derivative of a function who is a derivative of another one, that's going to be a second derivative of y. I don't need to do anything different, though, because the second derivative is just a derivative. So however I do derivatives, that's how I do it. So instead of feeding y to it, I feed y prime to this process. It's the same thing. It's beautiful. I kind of hate that the book makes it seem as if, okay, second derivative. Okay, here we go. No. You're just feeding it. What if I wanted an eighth derivative? I would just do this process over and over and over and over. Same exact problem. Whatever I get, feed it back. Whatever I get, feed it back. Sorry, there was a... Oh, sorry.
I guess I was just confused about the d squared y over dx.
Oh, of course. Yeah, of course.
I don't know how that got there.
So dy dx. So real quick, do you see how this is d this dt? So a better way to write is dy prime dt. So this is d by dx of y. So if I want to do it, if I'm going to do this again, this will be d squared y dx squared. So you guys have seen that notation before, right? No?
Yes.
Maybe.
It looks familiar.
I've seen it before.
Yeah, so this is just the second derivative notation. So all this is saying is that I'm doing, let me do this. So to this, I'm going to do another d by dx. Isn't that d squared? Isn't that dx squared? Just a way to kind of collect things. Yeah. Is that all right? So that's kind of old news, that how squared looks with this notation. Okay. All right. Nothing amazing about it. You just, if I feed the derivative process something that's already a derivative, I end up with the second derivative. Right? Okay. Gosh, tonight you just aren't giving me anything. Sure. Okay.
Maybe we should all wake up by doing the derivative of that thing.
Say again.
Hey,
Let's do
hey,
the
hey,
second-
he didn't say
second
anything.
derivative of that thing.
What's up?
Check
Let's do the second derivative of it.
All right, you can. All right. So does that answer your question about how to do it? It's kind of a bonus one though. All right. So what if I want to know the derivative at 0, 2? Do I have what I need now from earlier?
Yeah.
What am I going to feed to this dude?
The 1.
Yeah, so I want a y prime at t equal 1. So it'll be
3
3 over
pi cosine.
Negative pi.
negative pi. Kick ass, because cosine of pi is -1 times pi. So that's the slope at that point. Can you tell me what the tangent line is there? Easy peasy. Slope looks gross, right? Gives a shit. I don't give a shit. You know, like, yeah, you don't give a shit, because you got your
Like the
grade.
number?
No, I want to know what this tangent line is.
Oh.
Yeah, don't do anything of that. I don't want the decimal, but that's the best way to show this.
Okay.
What's the equation of the tangent line? Can't you do 1 minus y1? Or even better yet, that's silly. What's this?
That's the y-intercept.
Yeah, that's the y-intercept. So it'll just be -3 over pi x plus 2. Let's see if that makes sense. At 0, 2. At 0, 2. Well, from my picture, it's really, it looks like it's flat through there, but apparently it's not. It should be at a down arc. But oh well. So it would be 2, and then it would go -3 over pi is almost -1.
Minus 1, yeah.
Yeah. So it'd just be down 1 over 1, up 1 over 1. So it'd be like that. So my poor little graph does not look. That's the positive slope check.
Yeah.
That's better. Yeah, that looks pretty good.
Yeah.
Yeah. Okay. Yeah, but stop shitting on your graph, Jeff. Okay.
And it'd be a little closer to the, it'd be like a little bit above that 1 point, right?
A little bit above that 1 point.
Like the 1, 0 point on the graph, like the right side of it.
Here?
Yeah, like the black arrow would be like
Yeah,
right
at 1.
above it, or right below it.
You would have to have x.
Yeah, at 1, this would be like, yeah, it's gonna be right about there, I think.
Are you sure?
It's
Yeah.
almost 1.
It's all
Yeah,
side.
Okay. Enough.
Does
Yes.
the second derivative of this tell you the concavity then? It does, right?
It does.
Yeah, okay.
Yeah.
Also, a quick question. How come on the first derivative, we did the derivative on the top and the bottom, like L'Hopital's? But on the second derivative, you ended up doing like,
We did the exact same
we
thing
did the
we did
exact
here.
same thing?
We did the exact same thing.
Okay.
Didn't we have dy prime?
Yeah.
dt, dx, dt? It's the exact same process.
Okay.
Whatever function you want the derivative of, you put it here, right?
Okay.
Yeah.
You can do this with any function, even like the circular ones, as long as you're just doing it at a point, right?
You can do this for any parametric defined.
Any parameter. Okay.
Yeah. As long as it's not undefined, even if it's undefined, you know it's a vertical tangent line there, right?
Right.
Okay. All right, maybe. It's a very strange vibe tonight. Okay. Okay.
It's close to fine.
Let's see. What about, length of an arc? Yeah.
Arc length?
Arc length.
Like the stuff we did at the Cup one.
Alright, so everybody got what they want out of this? Okay.
Yeah.
I guess I could do
I don't
this.
remember
Well,
any of
shoot,
that.
Let me see. Let's leave this up here for a second.
Yeah. It's fucking weird.
Alright.
Come on, Jeff.
How did they write it? I don't either. Okay. I'll write it the same way.
I don't need it at all. See y'all.
don't know if you guys remember this from Calc 1. My students, we looked at it.
Yeah.
Anybody else who wasn't my student, I have no idea if you guys did. This is from chapter 8. So this is the arc length of some function. Right? So very quickly, if I have just some arbitrary function, and I want to know how long this is from there to there. That's a little difficult because it's not a straight line, right? So I can't just do it as a crow flies. So what I do is I zoom in and I say, okay, so if I zoom in on this point and I go dx and dy, right? So if I zoom in on that point, wow, and I have this, so this is dx, dy, right? That little element that it describes is a straight line. You guys, when you zoom in enough on a differentiable function, it becomes linear. It's the idea of local linearity, which is the idea behind linear approximations. Okay, a lot of stuff coming together right now. Right? Sort of like the Earth is curved, but it looks like it's flat because we're really close to it, right? Okay, I like it. Of course, we're all college educated, so we know it's not flat. It's not flat.
Okay,
You
kind of
think it's
political.
flat? Keep it to yourself.
Don't really appreciate you forcing these opinions on that.
What?
Didn't know
My
liberal
professor's trying to
ideology.
indoctrinate us. And of course I did get the square there. Because what would I use here? I could use Pythagorean theorem to figure this out, and really it's just adding up each of those lines, right? Okay, so I'm not gonna go through the whole derivation for that, that's from before. So now if I have something defined parametrically, I would want to do something like put this dy dt over dx dt, right?
Oh.
Just to start to bring in this parametric stuff. True. Let me see. How do I do that? Oh yeah, that's true. If I want to make it like that.
For the arc length, or by integrating
Oh,
it?
that's right. I need to do that. That's right. Huh? Say again?
For the arc length, by integrating it, are you also getting the area? Are you really measuring the area under the arc, or the arc itself? Like how long the arc is?
Area under the arc. Oh, no. Just this by itself. So if I have, so for example, if I want to know how long would I travel if I followed this path,
Okay.
right? I drove much more than just 6, right?
Yeah.
I traveled. This process would tell me how long that road is.
Okay.
Is that cool?
Yeah.
So it's the idea of displacement, displaced by 6 here, right? But how far did I actually go? Oh shit, I don't. Maybe. So see how I have things in terms of t now? So I kind of want this to be in terms of t. So I can do a little finagling. I can kind of do this. Is that true?
Yeah.
What does that reduce to? Doesn't that just become dx again? Right? And then I can bring this inside. And by the way, I left these blank because now what's my variable now? Here is x. X goes from A to B. Now it's t, so of course we're going to use funky ass Greek letters. Why not? Just to differentiate.
What's the bottom one?
Say again?
What's the bottom one?
I'll fish.
Alpha.
No, it's alpha.
Okay.
At least.
Alpha, beta, yeah.
Yeah, that makes sense. It should be.
Okay. Real quick, is that cool, right? Isn't that the same thing?
Yeah.
Yeah.
But now if I bring this in, do you see how I've made it an integral of dt?
Do you have to do that for this?
For certain specific types of problems, you might not have to. For the generic problem, you need to, yes. So, let's see. Real quick, if I bring this in, dx dt is the square root of dx dt squared, yes?
What did you just say?
Right? dx dt is the square root of dx dt squared.
Yes.
And then I'm allowed to bring it in because now it's the same root. It cancels here and it shows up here.
You said that fast, and my brain just exploded.
It was a very soft explosion, so I appreciate that. Nothing came out. That's good. I'm glad you kept it contained. Clean it up later. You're highly responsive for it. It's great explosion. Okay. Sorry, I'm laughing at your injury. So, let's see if we can do this. So if I wanted to know how long this segment is, we already know what T does. What does T do? From the beginning we knew. It goes from
0 to 2.
0 to 2. So let me delete this from earlier. We don't need you anymore. Get out. I sort of needed it. That's all right, Jeff. So it's going to integral from 0 to 2. That's what T does. Square root. What's dx dt squared? What's dx dt? This is probably going to be something we can't do, or I really don't want to do, but I just want to show you how to set this up.
Pi cosine by t.
Say again? Yeah. This will be pi cosine pi t squared. And then dy dt is nice. Now, real quick, is that an integral?
Thank you.
Is that an integral that we can do?
That you would want to do?
Not. Well,
We
no.
could probably do it.
I like that.
I see the vision.
We have a lot of tools, don't we?
Yeah.
Until we try, you don't know. Well, let's not. I really want you to understand. This happened to us too also. I don't know if you guys remember back in Calc 1. This process, since it has this big ass square root, unless it's like a trig sub or something, this could lead us to integrals that are very difficult to do. This is not just the square root, it's got a trig piece and the polynomial piece inside. U sub won't get us anywhere. By parts won't get us anywhere really, because this whole thing is one part. You can't let U equal a piece inside. You have to let it equal this whole damn thing. I really want you to understand. We could probably do some things and get somewhere, maybe. But it would be really, really gross. So I think when I assigned the homework, I tried to pick the ones that would end up with integrals. You could actually do some substitution kind of stuff too, and so forth, right? Okay, I guess I'll find out when you do the homework.
One of them, it all cancels out.
Yeah.
It's fun.
So some functions kind of work together well. These two do not. And by the way, the problem didn't ask to do this. I just added this on, just so I can show you a setup for one of these. Okay. Blah blah blah. Okay, there's that. That pretty much finishes 10.2. It's page 653 where they have this thing sitting, this form here. Yes.
So, just to clarify, that's telling us the length of that whole squiggly line.
Yes. If I do this integral, and actually you could just plug this in your calculator,
Yeah.
right? You can just plug it in your calculator, do second calc, or do calc number 7 for integration, right? The number you get would be how long this is. Yeah.
That's pretty cool.
So if I did it to something like this, I wouldn't need to. I can figure out how long that is because it's a straight line. But if I did this process to a straight line, it would tell me how long it is. It would match with what we would get anyway. This, I need help. It's curve in, right? It's not straight. So the curve makes it go further than a straight line here. And how curvy is it? Do you want to do a second derivative? And how quickly is the curvature changing? Do you want to do a third derivative? No. So this process will actually just tell me how long that is. Yes?
So for clarification, for the second L thing down, the fish and the double S, when you take the dx dt, you're basically just squaring dx dt and putting it inside.
Yeah, well, I can't multiply something without a root into something that has a root. So I just do this.
Okay.
Then I'm allowed to multiply this in.
Okay, that's
And it
good.
cancels with that, and it shows it there. Shlabam. Okay. I like it. Okay. Not a huge part of this class, but it's in there. It's something we can do with parametric. I love it. All right, erase this whole thing. What gets more interesting is finding the area. Am I too soon for this? Maybe. I thought they did that. No? No. Well, that's good. No, here it is. Okay, beautiful. So if I'm given a parametric curve, let's say I had one that looked like this. Right?
Would it be alpha?
Say again?
Because it's parametric, would you be using alpha and beta? Or
Well, that's on the x-axis. So that's A, B.
So when it's on
I
the
don't know what
orbit-
T is at this
Oh,
point.
okay, so
Yeah.
when it's a T graph.
That's a good point, yeah. So T here could be 107, and there it could be 18 billion. I don't know.
Okay.
18. Okay. Okay. Stop for a minute, you guys. Semi with me?
Sure.
How do I? If you had to explain integration, so when you say, okay, you have a function, blah, 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 and you're A to B, and integral f of x dx, right? From A to B. Right, you would include more words,
You're
but
finding
wouldn't
the
you
area.
use that to kind of lead somebody down to,
Yeah.
right? It's not explaining what an integral is, but explaining kind of how to set it up and do it. F of x is just another letter for y, correct? So, up here, I've got x is some function of t, and y is some function of t. And that made this picture, right? And I want to know the area enclosed in there, right? Sounds very familiar.
Yes.
Okay, so I would want to do this, and I would want to go from, well, here's where things get interesting. So this would be A to B at the moment, because that's what x is doing, correct? What is y?
G of T.
G of t. What is dx? Oh shit, what is dx? dx is
F prime of C.
f prime. I didn't do a u sub. Du equals misdis dx, right? So what is dx? F prime t
Oh, DT.
dt. There we go. Kick ass. So I replaced that with. Now it's talking about t. And what's t doing? I don't know, going from alpha to beta. This is huge. When I teach Calc 1, and you guys can vouch for me, I try to make a big deal, especially when we get to volumes of solids, of revolutions, how important this shit right here is, right? If you're doing disks and you're rotating around the x-axis, you use dx and dy. Remember all that? The first step is this, because then that controls everything else. So if I see dx, these have to be what x is doing. When I see dt, these have to be what t is doing. Why do I use different letters? Because t doesn't have to be doing the same thing x is doing. Of course it doesn't, right? T's its own thing.
Oh, dang.
That's right. Ain't nothing but a chicken. Okay. Let's do an example. Let's see. I don't know. I'll pick one out of the book, because if I try to make one up, we'll get all freaky. Bum, 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 bum. Bum, 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 bum. Blah, blah, blah. Give me a problem. Find the area, here we go. Oh, okay, well. Okay, let's try this one. I think that's the problem I gave you. Let's do that one. Find the area enclosed by the x-axis. And these two, and this set of parametric equations, this curve tq plus 1, and 3 is my nemesis. You guys are like, no, English is your nemesis, John. 2t minus t squared? Is that what that says? Yes. So it wants to find the area enclosed by the x-axis and this curve. So I want to know, all right, how am I gonna figure out what that looks like? Maybe I should start graphing this thing, right? So if I do a txy, try to be smart about this, flesh
Thank you.
Do you see how the y values, if I factor that, do you see how the y values are gonna be positive between 0 and 2?
Yeah.
Right? Okay. So let's try this. Either you can do a complete picture and try to do the whole thing, or we can try to figure out when is it gonna pop its head around the x-axis, when is it gonna show up. So when y is 0 is when it's on the x-axis. So that's good. Where's y 0?
Negative. Wait,
When is y
Positive
0?
2. At t equals 2.
2,
T equals 2, and?
0.
T equals 0.
Right, so let's do a few. Let's do one in let me check. Say something and then do it. Okay. All right, mate, I really want you guys to do it. It wants me to find the area enclosed by this curve and the x-axis. So doesn't it make sense? I want to know when this curve hits the x-axis, right? But in general, if it's like, tell me the area enclosed by this function and the x-axis. Well, I want to know if it hits the x-axis there, is it like that? Is it underneath? Then I can find this area, correct? I can even find what to go from to. When does something hit the x-axis? When y is 0. So I can see very easily when y is 0, right? So then I can focus my attention on 0 and 2 and in between. So when t is 0, what's x? 1.
And h.
And of course y is 0.
Yeah.
When t is 2, let's do 2 real quick. Y is 0, of course it is, because that's how we got to.
And x is
And x is
9.
9. And when t is 1, let's just do something in the middle just to kind of give us one more anchor. When t is 1, x is 2, and y is 1. Okay. So I get, I've got to go up to 9, damn it.
Can we just like skip a few?
4, 6, 8, 10. So I got 1, 0, 2, 1, and 9, 0. Here. Okay. So it looks like that. The arrows you don't really need in this problem, but still. Okay. So now this is relatively easy. And again, I would think about this, and then it's really just whatever the y function is times the derivative of whatever the x function is, because that's how I do an integral y dx is how we do it. So this is going to be the integral from what to what? Because it's d what?
dt.
dt.
So from 0 to 2.
0 to 2.
So it's just y times.
So what the y function is 2t minus t squared, right? Times the derivative of the x function,
3t squared.
3t squared. All right, so if you had to choose an integral to be graded on,
This would be
that would be a pretty good choice. Yes? Yes?
Sure.
I just have a question. Where did the 3t squared come from?
Oh, so see how this requires me to take the derivative of x? What is the derivative of x?
Oh, 3t squared.
Sweet. So if I were you, I would even just remember this form, right? Just remind yourself it's got to be dt at the end, so these should be related to t. But y, okay, whatever the y is, bam, dx, okay, whatever the x is, the derivative of it. Maybe? Because this is basically every integral you did in Calc 1, right? Integral of y dx is what almost every integral in Calc 1 was. Okay, maybe. Not too bad, right? Really, really not too bad. Well, I don't know. What is this? I almost don't care. Let's see. The interesting stuff's over. Now it's just, doing this shit. 6t cubed minus 3t to the 4th. That would be 3/2 t to the 4th minus 3/5 t to the 5th. Right? From 0 to 2. That would be, I think it'd be 24 minus
96 over 5.
96 over 5, so yeah, whatever that is.
24 over 5.
So it'd be 24 minus 1. So what's this? Is that cool? It'd be 24 minus 24 fifths? Watch this, this is cool. A whole 24 minus a fifth of a 24. 5 fifths of a 24 minus 1 fifth of 24 is 4 fifths of a 24. So it'll be 96 over 5, right? Yeah, okay. And you're all like, whatever, man. You just plug in your own calculator or something. Yeah. Maybe. It's not that bad. It really isn't as bad as you might have thought integration with parametric curves would be. Yes.
Maybe I'm just, I don't know. The bottom correct. Can you explain that again?
Which bottom part? This here?
Yeah.
So here I just multiply this
Oh,
through.
you will play it
right?
out.
Yeah, just multiply that in.
Oh.
Yeah.
Yeah, I'm going slow.
Yeah, cool. Okay.
Same portion, that first exponent, that's a 3.
This here?
Down.
This here? Yeah, anything you're not sure about, it's good money that it's a 3.
Okay.
Yeah. Yeah, 3s are definitely my nemesis, although 5 is not too far behind.
Oh, what a nemesis.
Yeah, I got a lot of.
It's actually pronounced
The
nemesis.
worst is when.
Your nemesis is my writing, that I understand.
That is.
You wanted a teacher you could read what they're saying, you chose poorly. Yes.
The worst is in textbook problems when they give you s's as a variable and you have to write 5s as well.
Oh, I just changed the variable immediately. Holy crap.
Or T's and plus signs.
Yeah, I finally learned to do T like that. Now it's just habit. Because I was doing
Yeah.
T's like this and it was plus T.
That was all my life. When that's literally when I
T
got
plus T minus T plus, holy shit.
Oh.
Right? No. So you learned to make T's like that, yes.
When I got to pre-calc, I started to like train myself.
Oh yeah, you definitely need something, dear God. Okay. Not that bad. If I were you, I would remember this, because then it goes right along with the way we're given it. This form really doesn't help, it just kind of reminds you it's dt at the end, right? Okay, maybe. All right, okay, so let's get into polar stuff. I don't think we've talked, have we done much with polar yet in here? I think I focused on parametric.
I don't think we did any
We haven't done
polar.
it
We did.
before.
Okay, so I want to kind of do the basics of polar, and then like on Monday, what's happening Monday?
Quiz.
Yes, quiz instead of a test,
On what
right?
What's it on? Yeah.
It's going to be on.
Oh, wait.
That's not ideal.
To be really honest, I could only make it on 10-1. Yeah, because
Really?
I never give a quiz the next day after we finish talking about an idea. We just finished talking about section 10-2.
So- Section 10.1 isn't really even like.
Yeah, I guess we did talk about the derivative. So I'll tell you this. It'll be 10-1, and there will be a derivative problem, right?
Okay.
Because we did talk about that before. But it's only going to be the derivatives. It's the very first thing 10-2 talks about, right? The dy dx is dy dt over dx dt, that thing, right? So the quiz on Monday will be parametric, and it will have one calculus question. So it's going to be mostly graphing and eliminating the parameter, right? Basic stuff, and then one derivative kind of base question. Okay, so let's look at this sheet. Let me know if you need this sheet, the polar coordinate sheet. Everybody got that? Let me put it up here. Oh, you need? Okay. Yeah, I feel you on that. Alright.
It's cold.
Today's lecture
Cold?
brought to
I'm
you
like
by-
sweating right now.
So
You're sweating?
We're getting ads for like.
I kind of want my sweater.
Guilty?
They don't sweat, JP.
Smile. Jesus.
Alright, let's see.
I mean, I'm not like
Gross and
cold
moist.
sweating. I'm just like warm. I'm not actually sweating.
Then take your hoodie
It
off.
was an expression, okay?
Alright, guys.
He's nervous.
Enough with the sweat.
I'm tired, I'm ready to go to sleep, my body's shutting down.
What?
Said ours.
Are your arms heavy?
Knees weak.
Vomit on your
Spaghetti.
sweater already?
It's mom's spaghetti.
I can smell it from here.
Alright, I love you guys. End this really awesome conversation. Okay. So we didn't do any of this, is that true?
Yes.
You gotta excuse me because I'm doing the exact same freaking worksheet with my pre-calc students.
Oh, that's cool.
I know.
Is it chapter 10 as well?
8, isn't
In
it? Oh, pre-calc.
pre-calc, I used an open source free textbook.
Oh,
I don't know
that's cool.
what chapter was in the other crazy ass expensive freaking textbook. Okay. So did I at least set up the idea?
No.
Holy shit, okay, let me start. Let's start there. Okay, real quick. I'm not gonna spend a ton of time on this. Thanks. You got it. Okay. Because I know some of you guys have not done much with Polar, or maybe not at all. So Polar's, alright.
The plane goes this way.
Remind me, how many of you guys are gonna take Calc 3? Anybody? Okay, ooh, okay.
Oh, dude. I think I bet you.
Calc 3 is where you start to learn many more coordinate systems. How many coordinate systems are there?
A lot?
About as many as there are mathematicians.
Oh.
Oh,
They all make their own?
How many families of coordinate systems are there?
4.
A lot. But
Did
then
you
there's
make
all the coordinate systems you can make with little tweaks and stuff. So in Calc 3, you're gonna learn the polar coordinates, so isn't that 2D? You're gonna extend it to 3D. You can either
Okay.
do it with cylindrical coordinates, or you can do spherical coordinates. Dude, where you have a sphere's radius and then 2 different angles that describe all the points in 3 space. So the XY or the XYZ was the most natural thing to start with.
0.
But, say again?
0?
0? Sorry?
What?
Isn't
So-
that what you're asking?
No, I didn't ask you a question. Sorry. Let me try again. So the XY and the XYZ coordinate system was the most natural one to start with. But there are problems that are really difficult to do in a coordinate system that's set up for frickin' boxes. XYZ is beautiful for rectangular boxes. Yes? Go this far, go that far, go that way. That's a frickin' box. So what if I have curvy things? Okay, maybe I want to use spherical coordinates. And then my interval will become stupid nice. So if you take Calc 3, a lot of you guys look like you're going to take Calc 3, you will see exactly what I'm saying. You will have these things that are impossible to do with XYZ, and then you change it to spherical, and it's like, bam, 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 no problem, nothing wrong. Okay, so polar, so instead of finding a point by telling somebody to go so many over and so many up, that's what we do with XY, correct? So I often think of this as, for example, I always pick on Utah, because I remember going to see a friend of mine in Salt Lake City, and did I tell you guys this? It's so grid-like in Salt Lake City, it almost, I'm a math guy, but even there I was like, this is just too grid-like. Because I'm used to Virginia Beach where roads intersect themselves, which is the complete opposite. So I can tell somebody to go so many blocks over and so many blocks up, and they get to my house, correct? In the ocean,
Where is this going?
in the ocean, can you do that?
No.
No.
Yeah, I'm on this boat. How do I get there, man? We'll go about 7 blocks. Blocks?
You use clicks.
Okay, sure, but that's a distance. You don't tell them to go so far on the x-axis, so far on the y-axis. What do you, even if you've never been in a boat?
Leagues?
But how do you move in a boat? Don't you set a
Very.
heading or bearing?
And then
right?
you measure it for time.
So if I told somebody, instead of doing this, if I said, turn through this angle, so I'm standing here, correct?
Mm-hmm.
Turn this much, and then go this far out.
For 30 minutes or
No, go that far out.
something. Oh.
On a boat, you could say, head this way, take this bearing for 2 hours or whatever, right? Or go this far on this heading, and that's where the island is, or whatever, the treasure, or the monster island. Okay. You guys semi with me?
Sure.
Doesn't that just So again, these are real life examples using these different coordinate systems. It's not x, y. So you got latitude, longitude, great, but you also have turn by so much and go so far.
So is it time and speed?
Okay.
Or is it speed to
I see it.
Just don't think about it like that. You're
Real quick,
just
guys.
Going to a place.
If I tell somebody to go this far and this far,
Yeah.
there is no question like that. It's just a distance to go, right? This, turn by such an angle and then walk a certain distance. Now I could start talking about derivatives. That would be velocity and all this kind of stuff, right? I could. We're not doing that yet. We will. Okay, I like it. So I can find points in two space, either using rectangular coordinate system, x, y, or the polar coordinate system, r theta.
No.
Can we create conversions between these? Well, let me do this first. Let's do a specific concrete example. So let's take something, let's say, well, let's just do this is 3 and this is 5, right? And there's a point. Can somebody figure out the angle and the distance I would have to go through to get to that same point?
The angle would be the inverse tangent of 5 over.
Yeah. Right? The angle would be the inverse tangent of y over x. And you throw in the old calculator, right?
Yeah.
And how do you get the distance? Pythagorean theorem. So r squared would be,
25 plus 9
yeah,
is
3 squared plus 5 squared.
34. 36. No,
36.
34.
34?
34.
34. I was right the first time. Root 34.
Okay, that was neat.
Yeah.
I like it. 10 plus 25 is 35. Okay,
Yeah.
okay. Right? Is everybody cool with that? Yeah, you can throw this in the okay. Can somebody do that real quick? Has anybody got the calculator?
59.
Say again?
59.
59 degrees? Okay. Alright. So I can tell somebody to go 3 blocks over, 5 blocks up, or I can tell them to turn by 59 degrees and then go and then walk out 34 feet or whatever it is, right? Or square root of 34. Okay. I like, which is of course the way that most tell people how to get around. Turn by this angle and then go the square root of 34. Okay. So in general then, what's theta? It's exactly what we just did. What is theta in terms of x and y?
Tan negative 1 y over x.
Right. So this is a conversion between rectangular, polar, right? And what's r squared?
X squared plus y
Yes. Okay. Right?
Damn.
Again, you guys see this on your page in red. You guys
Yeah.
see those? And of course, what's the connection the other way? What is x in terms of r and theta?
R cosine theta.
Yeah, r cosine theta. Y is
R sine theta.
And I think I've told you this before, have I? I think of, this is not true, but it's a cool way to think of this. Cosine theta is the percentage of r that lies in the x direction. Sine theta is the percentage of r that lies in the y direction.
How is it not true?
It's not quite true, but it's good enough. It's a good way to kind of remember stuff. And this is really good if anybody takes physics. You're constantly breaking vectors into components and putting them together. So a lot of this should look very familiar.
But you also use sine for the x value a lot in physics.
Sure. It depends on how you orient things,
Okay.
right?
Yeah.
You got multiple things going on, so cosine will not always mean x, but yeah. Okay. But for us, it will. Okay, so these are really basic computational problems. Once you know these, and you do have to know these, it's not that big of a deal. You already know freaking these, right? Isn't cosine x over r? Yeah, so you already know this shit. Okay. So if I wanted to convert, if I wanted to convert this to polar, how would I do that? I'm sorry, this to rectangular. It's currently in polar coordinates.
Mm-hmm.
What's 2?
R.
R. because polar is r theta. So theta is 5 pi over 3. So, sorry? Oh, yeah, thank you. Giving Adam an eye off. Being my cameraman. So real quick, come on, how would I make that into a rectangular?
You would find.
I could just use this, right?
Make the triangle.
X is 2 cosine 5 pi over 3, and this is everybody who doesn't know trig well, this is your recurring nightmare. What is cosine of 5 pi over 3? What quadrant is that in?
4.
That
Fourth quadrant, so cosine's gonna be
positive.
positive. Reference angle is pi over 3, which is 60 degrees. Cosine doesn't like it there, because it's far away from its home. So it's gonna be,
root 3 over 2.
no, that's when it likes it, that's big.
Minus 1/2.
So it's gonna be, no, we said it's positive,
One.
so it's 1/2.
Oh,
That's
1/2.
1.
So it's 1.
1.
Yeah.
Oh, man, axis.
X is 1. Y will be 2 times
It's gonna be root 3.
sine.
Negative.
Yeah, negative. So sine of 5 pi over 3 is negative rad 3 over 2 times 2 is just negative rad 3. Okay, so this point translates into this point in rectangular. Now, I'm gonna do this a little bit out of order, because we don't have to do this whole damn page. This is for pre-calc, and you guys are above pre-calc, so you should be able to, even if you've never seen this shit before, you should be able to like, get it. Let's see.
Yeah.
Look down here. I'm gonna plot that point, and here's how it works. What's my heading?
What?
What does heading mean?
Which direction will I
Oh,
face?
5
Oh,
pi over
5 pi
3.
5 pi over 3. So I'm gonna look at 5 pi over 3. I'm at the origin, I'm gonna look at 5 pi over 3.
And move 2 spaces.
And I'm gonna move 2 spaces out.
Okay.
You guys see that?
Yeah.
So these circles are your r-axis. You can change the scale if you want to. I just chose to do it by ones. So this could be 2, 4, 6 if I need it, right? If I need to go out to 14, I probably need to make this 3, 6, 9, 12, 15, and then I can go out to 14. Are you guys with me? So just like x, y axes, I can change the scale on these. The theta scale is pretty well set.
Can't really change that.
There's no reason to, and you can't, so great, those match up great. You can't, oh shit, there's no reason to, oh good, okay. Now real quick, can you guys see the x-y axis here?
Yeah.
Isn't this 1? Do you see how that's 1?
Yeah.
So see how that's 1? The x piece? And the y piece is between 1 and 2? Maybe roughly square root of 3 like we said it was supposed to be? So again, this isn't just an exercise in can you throw shit in a trig and get answers. This is actually that point that you can get to by looking a certain direction and walking. You also can get to by going over and down. So when it converts, it's the same freaking point. You guys semi with me?
Sure.
Sure? So what was this point again?
1 negative, right? Or 1.
What is it?
1 minus
2?
5 pi over 3.
Does someone have another way to say that point?
1.
1 comma negative square root of 3.
negative
1.
square root of 3. Or in,
No, I mean in polar, sorry.
Oh.
Another way to say the point in polar, sorry.
Oh,
2 comma 270 degrees? Is that what it is? What? No, what is it?
No, I don't care about
We could
degrees,
do,
keep it at
we
radians.
could do
Oh.
negative 2,
Yes.
3, no, negative 2.
Negative
2
There it
pi
is,
over
negative
3.
pi over 3.
Right? Would it be 2 pi over 3 or?
No. How far away from 6 pi over 3 is 5 pi over 3?
Oh wait, no, I was thinking doing the 2 negative.
I really want you to understand, so I could either have somebody turn 5 pi over 3, or I could have just said, oh, just turn the other way by pi over 3, right? So how many ways is there to label a point in polar coordinates? No, there's a lot more than that. How many ways? is there?
Infinite amount of ways?
Infinite number, because I could just rotate a billion times, right? And real quick, this morning I said this to my pre-calc students. because I like to point this out, because as a pre-calc student, when you first learn trig, and you're like, okay, the stupid thing, like get the same point, plus or minus 2 pi k. Remember plus or minus 2 pi k, anybody?
Yeah.
When you have all the solutions, and you're like, it's the same stupid point, what the shit? But if I add, that's exactly how this happens. If I add a z-axis to it, then it's sort of like those parking garages where you have that spiral drive that you go. So now when I do a full turn, I'm at the same place in terms of here, but I'm up 1. So I did a complete circle, but now I am actually physically up. So doing a complete circuit, I get the same xy point, but my z point is higher now, right? I just want you guys to realize, when we're in 2D, we're very limited, obviously. So a lot of this stuff doesn't make sense. But the minute you kind of give yourself another dimension, now it's not really repeating itself. It's actually, in this third dimension, it's actually going up. Maybe? Okay, all right. Look here. Yeah, it's good. That's the same thing, right? I mean, once you see one of these, they're all the same. Yes? So this one, I've got an equation. I want to make that equation become rectangular. What do I wish was in front of the sign? Because then it would directly become one of the rectangular variables. What are my rectangular variables?
R.
X and Y. No, polar is r theta.
Yeah.
Why do we call it rectangular? Because it's really easy to make a rectangle in x, y. Yes? Okay. What do I wish was in front of the sign?
R.
I wish R was there, because what's our sign?
X.
Sagittarius, though.
What?
It was, what's our sign?
Is that your sign?
No, it's not. Sorry. I don't know, I was just guessing in case somebody was, and they would go, holy shit, how does he know that? I really want this to make sense. So I want an R here. If there was an R in front of the sign, it would be Y, correct? I could just put a Y there. There's no R there. So how do I put an R there legally?
You gotta multiply. You gotta
Oh, I see.
multiply R.
There's a better one. Just multiply both, yeah, I think you just said it, maybe. Multiply both sides by R.
Both sides?
Can you multiply one side and not the other of an equation?
No.
Okay, so that's what I meant by legally. You can just put an R any damn place you want to in math, but it's probably not gonna be legal, right? Okay? Don't do it, kids.
Don't put the R's, there's not even one.
So what is R sine theta?
R squared over 5.
Y. No, come on, what is R sine theta?
It's gonna be Y.
It's Y.
Oh.
So it's
And what is R squared?
X squared.
what?
Did we just take the equation and turn it fully into rectangular?
Yeah.
Totally, okay, good, we're done.
Wait.
You are hoping R squared shows up. You're hoping R sine or R
Wait a
cosine.
minute.
What happened? Did that blow your mind? The most random things blow your mind.
It's always the algebra. It's always the algebra. It's never the calculus. The calculus is more.
We'll make sure everybody's cool with this. Do you guys understand? Guys,
Okay.
Guys,
I get it.
do you understand what I'm saying?
Yes.
Right? If I'm converting from inches to feet, I'm looking for groups of 12. I'm hoping there's a group of 12. That makes it easy. So here, I'm converting from polar to rectangular. I'm hoping R sine shows up, or R cosine. And if it doesn't, can I make it show up? Yeah, I could just freaking multiply by an R. And the other side became R squared. That kicks ass. I'm hoping I see R squared, because then that's awesome. What about freaking B?
Well, that's just tan pi over 6 equals y over x.
If I take tangent of both sides, what is tangent theta? In terms of rectangular.
Y over x.
Y over x. So let's take tangent of both sides. If I see a tangent theta, I can replace it with y over x, right? So let me make a tangent show up. Tangent theta is y over x, yes? What's tangent of pi over 6?
Square root 3 over 3.
Yes. And then I can, to kind of make this, I can make this a nice line, right? What's the slope of this line?
Square root 3 over 3.
Which is the tangent of pi over 6? Is that why we call them tangent lines? Holy shit.
Crazy.
That's where I thought your mind would get blown, but oh well.
Nah, we've been known that.
Okay, gotcha. You're like, whatever, Jeff. Alright. And real quick, what about this one? Does secant show up in anything in our conversions?
Kinda.
No.
Not really.
It doesn't show up directly, right? What shows up that's related to secant?
Cosine.
Cosine.
Shit. Not cotated. It's been a long
Can somebody tell me what I can do real quick to make
Just multiply by cosine.
multiply by cosine? Because then I got r cosine theta. And what's r cosine theta?
X.
X. So if I graph this, it will be a straight up and down line. Sing it. He says cute.
That's cute.
Oh, okay. Well, that's cute, Jeff. You and your math. That's cute. Yeah.
So let's say R was like 3 for like the first.
Oh, if r was just 3?
Yeah, no.
Oh, no.
Like it has like 3r equals 5 sine theta.
I'm sorry. Oh, here?
Yeah, like this 3r equals 5 sine theta.
Oh, then there would have just been a 3 in front of this. There would have just been a 3x squared plus 3y squared.
Oh.
Yeah. What is r equals 3? That's what I was excited about. What does that define? What is r?
Circle.
Yeah, it's a circle with radius
The
3.
radius.
So the equation of a circle in coordinates that are circular is easy. What is it in rectangular coordinates if I wanted a circle of radius 3? What's the equation?
X squared plus y.
X squared plus y squared equals 9. It's not even freaking 3. It's a little worse. Not terrible, right? But it's definitely worse. You guys agree with me? Derivatives and all that shit is worse with x squared plus y squared equals 9. You with me? Not terrible, but worse. R equals 3. Of course it's just R equals 3. This is a freaking circle, and the coordinate system is circular. Yes? You start to understand. This is really far removed from what I'm talking about, but there are problems that are really hard in rectangular coordinates that are stupid easy in polar or spherical or something else. You guys kind of get a feel for that? Okay, okay. Okay, what else do I want to do? Blah, blah, blah. This should be easy, hopefully, maybe. I don't know. This here?
It's just tan theta equals.
Yeah, I mean, here I know x and y. So I'm going to want to use
Inverse
that to
tan.
figure out angle, right? So what do I need to know? I need to know r, that's easy. And I want to know theta. Well, that's the inverse tangent.
Yeah.
Right? Now, real quick, everybody. Okay, real quick. If I want to know the angle, won't that be the inverse tangent of y over x?
Which is pi over 6.
Yeah, we basically just did that one, didn't we? Why is that okay? Why is that the answer? What coordinate, which quadrant is this in?
1.
1, so that's the answer. 5 or 6 for theta, right? R is just freaking x squared plus y squared equals r squared. Easy shit, yes, I'm not even gonna do it.
It's a 30, 60, 90 triangle.
Usually. What about this one? This one you should, bless you. You should know exactly what angle that's talking about, or at least reference angle.
Pi over 4?
Yeah, it's gotta be some kind of pi over 4, but what quadrant is that point in?
The second quadrant.
Second quadrant, so it's a reference angle of pi over 4, so what's the actual angle?
3 pi over 4.
3 pi over 4, look at that, I didn't have to do much work at all,
It's a big pi.
right? Now, if you did the work, it would be the inverse tangent of negative thing divided by thing, which is negative 1.
Oh.
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 And if you do that in your calculator, you're gonna get negative pi over 4, and that's the wrong quadrant. So if you write that shit down, you're wrong. You guys understand? So this
Yeah.
whole idea about you have information about the quadrant, the point tells you what quadrant it's in. Of course it does. Okay, okay.
And then R's just 1.
Blah, blah, blah. And then this stuff is really simple. Hopefully. Maybe?
Yeah.
Because then you can just replace y with r sine theta, x with r cosine theta. What would you do here?
We do the same thing.
I wouldn't replace x and y with r cosine theta, r sine theta, because I could FOIL this out, and I'm gonna x squared plus y squared and other shit. And what is x squared plus y squared?
Oh.
R squared.
Yes. And so what would I do here then? First thing,
Same thing.
First
add,
thing?
Add y squared.
Add y squared, yeah. And what's y over x?
Tangent theta.
Tangent theta.
Ooh.
Alright, I'm going a little fast, but this is supposed to be a bit of a review, and it's really not that crazy. Okay, most of you look like you're okay. Okay. Okay, what's on the other side? Oh yeah, the other side I just gave you, there's the butt graph, just to get that out of the way. There's the Mesmero graph.
Are you taking bio?
Not
Relief
till
rows.
fall next year.
Right,
It's 2:30.
there's somebody's having some trouble, they should probably go see a doctor. Here's the peanut graph and the peanut that can't get together, okay. All those ovals of Cassini, you gotta love that. Where'd he go? There it is. Okay, anyway, I just wanna show you some shapes that could come out of these,
Do we need to know
these
these?
equations. No, I just wanted you to have this. You don't have to memorize them.
They're just cute.
They're just cute, exactly. This whole thing has been cute. Okay, what do you think?
Very cute.
Let's do one calculus related thing with polar, and then I'm gonna let us the hell out.
Oh, God bless you.
I am
I'm
freaking
tired.
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 I'm gonna do one thing. It's gonna take about half an hour.
It's like radiating.
Half an hour.
Ow.
Here we go.
I've been with you all day.
I'm excited.
Wow, you've seen each other since like 10:30.
No, it's too much.
I can't.
Yeah, yeah.
It's
not good. Absence makes the heart grow fond.
I got like.
What?
You wanna get the hell away from each other for a bit.
Because we see each other every day, man.
All right.
What's the last two seconds?
So if I had something, how do I wanna say this? Let me do it. Sure, okay. Let me give an example. Okay, let's say R is 1 plus sine theta. And I wanna know the derivative, I wanna know the slope of this thing. So we're gonna kinda do like we did with parametric. We're gonna start with dy dx, believe it or not. Because this does describe a set of points which could be called x point, xy points, right? So it's basically the same thing we did with parametric. Remind me, x and y are what? What's x in polar?
Cosine
Cosine
theta.
theta.
Our cosine, our sine. So what is dy? So let me do this way. dy d theta? Yes. Over dx d theta. Isn't that very similar
So dt.
to parametric?
Yeah.
So what is dy d theta?
Or sine theta.
Well, it's dy d theta. What's that? dy, y is our sine theta. What's the derivative of it?
Or cosine theta?
R cosine theta.
Oh, because ours is a constant.
Right. And what's dx d theta?
Negative R sine theta.
Sounds like Baxter.
Am I being too, what am I forgetting? Wait a minute.
There's like an addition part to it.
I'm being too, oh, of course, I'm being silly. Okay, I'm being too simple. I haven't included this idea. All right. So in general, oh yeah, that's what I forgot. So R is gonna be equal to some function of theta. It's way too simplistic. I was assuming R was a constant, which is not a good thing to do. So this is gonna be, X is gonna be some function of theta times cosine theta. Y is gonna be some function of theta times sine theta. There we go. So R is a function of theta, yes?
So R is a function of theta, but does the function have to be a function or could it be a constant?
Oh yeah, of course. If I say f of x is 5, what's the derivative of that?
0.
Nobody flinched when I said f of x is a constant, right?
Oh.
So a function can be a constant, yes. I like it. So that was a mistake I made. I forgot R, of course, is a function of theta. So when you do these derivatives, what do I have to use? Product rule.
Yeah.
So let's do
That's
this.
what I was thinking.
Let's keep R. I want to write this to remind us that it is a function of theta. So when I do dy, I have to use product rule because R is a function of theta. But let's keep R there. So I'm not having to write f of theta everywhere. So everybody, so I have to remind us R is a function of theta. So what's dy? It's going to be dr d theta times sine, doing product rule, right? Plus r times, so derivative of r times sine plus r times the derivative of cosine. Derivative of sine. Cosine. All right, we stop for a minute. You guys with me? I'm doing product rule on this. R is a function of theta, correct? So when I take a derivative with respect to theta, these are both functions of theta. It's a product rule. R is a function of theta times sine of theta. So I have to use product rule. Derivative of r with respect to theta sine theta plus r times the derivative of sine. We're going to do the same thing on the bottom. What's x? X is a function of theta times cosine theta. So I'm going to do the derivative of that with respect to theta, cosine theta, minus
R sine theta.
r sine theta. Okay. That's better, Jeff.
Oh, yeah.
It's better because it's worse. So if I want to do for this guy, all I have to do is throw these in. Any specific R I'm given, I've already got the end result. Oh, you're different. Oh, okay.
That's cute. So many cutes today.
It's cute, sure. So what is dr d theta? Nice and easy. Dr d theta,
Cosine theta.
cosine theta. So I get sine theta, cosine theta is equal. And here I would put r, which is 1 plus sine theta. Cosine theta.
Ooh.
And then here dr d theta shows up again, which is just cosine theta times cosine theta, so it's cosine. Ooh, you're just a
He's a squeaky boy.
squeaky boy. Minus r sine theta, so it'll be 1 plus sine theta. Sine theta. You guys with me? Okay, and again, it's just a plug and chug thing, yes.
So like, how did we get the whole like, can you explain the whole R as a function of theta thing again when you're doing the
So right here, this is what, I was focused too much on these, and then I was like, wait, there's a whole thing I'm missing. And it's because, is R a function of theta? Is R a function of theta? Yes, it is. So if I take a derivative with respect to theta, R doesn't just stay R, I have to actually take its derivative. I sort of like implicit, but I don't want to say that word, because normally that has negative connotations. I don't know. Implicit differentiation?
I don't even know what that is.
That's actually a good reaction. I like it. That's not a good reaction. That one makes me cry.
Yeah.
Now, I can keep going real quick, guys.
Wait, how do you go from the function dr d theta, et cetera, down to this green
You're just
function?
multiplying it by sine.
What's dr d theta? It's cosine, right?
Oh.
Times sine. I just wrote it like this because it's the next step.
Okay.
Do you guys see if I distribute this, I'm going to get cosine theta, right? Cosine
Plugged
theta,
in DRD theta.
right?
Yeah.
Plus 2 sine theta cosine theta. What is, you guys see that? Sine theta cosine theta plus sine theta cosine theta. What is 2 sine theta cosine theta? Sine 2 theta. Yeah, somebody knows their freaking.
Right when I thought I was out.
Pull me back in. So down here I get cosine squared minus sine squared, yes? So I get cosine squared minus sine squared
Which is
minus sine theta.
so that's
And of course cosine squared minus sine squared is
cosine.
cosine 2 theta.
Wait, it's still going?
And what else can you do with this?
I genuinely, I dozed off for a second. I wake up and this is what I'm seeing.
That sucks for you.
It really does.
Alright, so now if I wanted to know the slope, I don't know, what's this? Is this problem say that I think? Where did I get it from? My goodness, Jeff.
I expected this to be easier because
There it is, okay.
It looks easy.
Find the slope of the tangent line when theta is pi over 3. Now it's easy, yes?
Mm-hmm.
If I want to find the slope of the tangent line, I just put pi over 3 in. Easy peasy. Semi okay? Semi okay?
Like, there's just a lot going on. Like, it really, it's so extra for no reason.
You go to the last part, you just completely missed it, still right?
So this is given to me in the problem. It wants me to find the slope of this when theta is pi over 3. Which makes sense, because what's the input for this function? What's the input for this function? What's the input for this function? No, what's the input?
Theta.
Theta, right? So in normal f of x stuff, the input's x. And the problem would say, find the slope of f of x equals x squared minus 3x at, or when x is 3, right? So I'll just plug a 3 into the slope that I get and get the number, yes? Same thing here. Plug a pi over 3 in, get the number. They'll tell me what the slope is there. Yes?
So you're putting pi into 3 to the final
Plug pi
equation.
over 3 in, yeah.
Okay.
Cosine of pi over 3 is 1/2. Sine of 2 pi over 3 is going to be square root of 3 over 2. You're in the second quadrant. So forth. Maybe? Where did I lose you guys? I lost you guys somewhere. So real quick, go ahead.
If we were still using the boat analogy, like the derivative would be like the speed of the boat?
Oh, yeah, if I'm defining trajectory of something using this, this is a little bit weird because there's no explicit time dependence.
Okay.
This is just, so this isn't really gonna be, so as my theta changes, r changes like that.
Okay.
So like at 0, r is 1, yes?
Yeah, so like the amount of distance it takes to get there.
Because the sine of 0 is 0, right? At pi over 2, what's r gonna be?
It's gonna be 1.
1
2,
plus
so-
sine of pi over 2,
yeah.
what's sine of pi over 2?
1.
1, so it's gonna be 1 plus 1, 2, right? And as it goes, it's just gonna grow, so it's gonna go like that, right? Maybe? And then if I go into the next quadrant, sine is gonna shrink again, yes? Maybe, okay. Maybe?
So with the, do you have an answer for this that we can look
Oh,
at?
I don't know, we have to
It's
plug the
plug it
solutions.
in, okay.
Yeah. Just plug it in. What do you get?
I got -1, that might be wrong.
And let's see, watch. Pi over 3 is roughly there, right? And isn't the slope there?
Positive.
What's the slope there?
Negative.
Negative.
Yeah.
Right, isn't that
Oh,
slope
oh,
there?
oh, right, okay, yeah.
It can't be -1 though.
I don't know.
Because it's not.
It's
pi over
close to
4.
that,
It would
though.
have to be-
Negative makes sense to me, because that would certainly be a negative slope.
Yeah, but it's not 1, because that'd have to be pi over 4.
I don't know. You have to just plug shit in.
That's
See what it
negative
is.
1.
Is it? Okay.
Well, yeah, because it's going from 1 to 2. It's not going from 1 to 1.
Yeah.
Okay.
Definitely.
Alright, yeah, you get every slope between, because this slope, and then it can get all the slopes, because right up here it's gonna be flat, because now it's gonna start to come back. Yeah. Okay. I think that's enough.
Yeah.
That's enough. So, next time we'll have the quiz first, just on section 10.1 with one derivative problem from 10.2. We'll finish up chapter 10, and whatever time we have left on Monday, we'll start looking at the practice final. Cool. All right, guys.
You said practice finals already up, right?
It's up on Canvas, yeah. So, if you need a copy from me, just come by my office.
Raise his hand.
Analogy.
Get out.
So it looks like you're